Right now there are 68. 68 are there.
They are faculties or students?
They are faculties. Mostly they are faculties and student as well. PG plus PhD student.
Okay.
Postgraduate plus PhD students.
Okay.
And most of faculties. And that to be from across India.
Okay. Okay.
Okay. So good afternoon all. Now we have another distinguished expert with us. So just let me introduce Dr. Vikas Kumar sir. Uh, Dr. Vikas Kumar has completed his PhD from Thapar University and his postdoc from University of Nebraska, Lincoln, USA. Sir has been working with CDAC, Center for Development of Advanced Computing, Pune, CDAC, as a principal technical officer, and his field of interest is mainly modeling and simulation in CFD using HPC, high performance computing. He has worked during his PhD on a topic studies of heat transfer characteristics of heat pipe, heat exchange under natural convection. And during a post PhD, he has worked on development of 3D CFD model for cooling of eggs under forced convection condition and experimental validation of CFD model. His area of interest includes numerical and experimental heat transfer, then the fluid flow, the computational fluid dynamics simulation, and the high performance computing. Sir has a number of, in fact, large number of research publication. So I'll request participant to please go and look at his profile on a Google Scholar and on the web page of you can say that CDAC website. He is also having an academic collaboration with IIT Bombay, IIT Kanpur. Uh, so, Sarah, firstly, I like to thank for accepting our invitation. So this is a AICT sponsor 5 days program where faculties and PG student and the PhD scholar across the country they are participating, and uh, we are expecting that they will get the insight on computational fluid dynamics, various areas on logistics. So thank you very much, sir, for accepting invitation, and I like to request to take on the session, please.
Thanks, Professor Sonane. Okay, I will start. Good afternoon, everyone. And I am going to talk about high performance computing and its role in CFD. When we say high performance computing, what it means? It means that suppose if we want to run a very large simulation, maybe of the order of 100 million cell size. So when this type of problem you cannot solve on the desktop or even on workstation, for solving such a large problem of 100 million size, you require a high performance computing platform, which may have say 1000 cores or 10 or 5000 cores. So that is what it means, that solving a large problem with the help of means a large number of cores. So with this, just I would like to go through my presentation, and if you have any questions that you can write down and we will discuss at the end of this presentation. Okay, my slide is. Just a moment, slide is not moving. What it is?
Sir, move this cursor on bottommost part of your PPT. There are
Here?
like signs will be there. Shift, yeah, just down this left hand side, downmost corner.
Yeah, here?
Here.
Here?
Downside, left hand side of PPT.
Here?
Just do one thing, sir. Click right hand side of mouse. Just click right hand side of mouse.
I don't know. It is not. Okay.
Okay. Thank you.
Okay. Anyway, okay. Okay. So I would like to talk about at CTEC what are the different research areas, and then I will talk about what are the different CFD applications that which we have done using HPC. So hence onwards, I will use the term HPC for the word high performance computing. At CTEC, we have application development group. In the application, HPC applications like weather modeling, weather prediction, bioinformatics, CFD, and seismic data analysis. So these kind of things, applications, they require HPC. Then high speed network means, suppose here you can see there are different number of servers are there. So all the servers, they talk to each other. And how do they talk to each other? They talk to each other through the high speed network. Then there is another research area that is called the reconfigurable computing. In the reconfigurable computing, basically this is a customized hardware and software for a specific application, like fast Fourier transformation or solving some typical bioinformatics problem. So for such a specific type of problem, we use RCS kind of tools. And then system software. Then of course, for supporting such a large say servers, and it's for job submission and login different users accessing this machine, for this system software is required. Then industrial design and engineering group is there, so which is basically engineering how the different servers, how it will be arranged, what will be that cooling layout, how the different where the crack units will be placed, and then HPC management and operation, and then there is a group which manages the HPC facilities, and then how the different computing servers, how they are connected with the grid, and then HPC solution groups. These are the different groups which are working at CTEC. And then here we say that actually how we have evolved over the period of time. In the HPC area, we started way back in the 1991 when we didn't get Cray computer from USA for the weather modeling weather applications. And after that, we started this journey, and this shows how we moved from 1991 to 2013. In the 2013, we have currently CTEC is housing this Param Yuva 2, which is a hybrid computing platform. When we say hybrid computing platform, it has the different kind of that hardware architecture, like that is Intel mic, which is a co-processor, and then FPGA and GPGPU, that is a graphical processing unit, which is supported by NVIDIA. At CDAC, we have also worked on the Garuda Grid project. So actually this project, the idea of this project was that if there are different computing resources, then how they can be connected over the network. And for this, actually that if you see that there's an NKN network, it was used for connecting the different servers across the India using this. And this Garuda Grid, it was having a computing facility of 75 teraflops, in which all the different HPC resources were connected over the in this grid. And it was having 70 partners from the academic and research institutions, which help scientists and researchers to carry out the work. I talked about this Param Yuva 2. So it has this Param Yuva 2 is operational at Pune University campus premise, and it has total 224 nodes, and each node has a memory of 64 GB, and on it is all these nodes are connected through InfiniBand, and it has co-processor, that is Intel Xeon 5, and it has also at some nodes we have the GPU computing facility. Yeah, this is what we are talking about, the different scientific and engineering applications, where this HPC will be used in the life sciences drug discovery applications, and for ocean, earth surface and atmospheric modeling, for weather forecasting, CFD, disaster management, discovery of new material, means the chemistry people are also using it, and this seismic data processing for the extraction, for the oil extraction, and these are the different scientific applications where we need the HPC computing facility. Regarding challenges, when we say that when we use HPC in CFD, that CFD is one of the largest user of HPC in the engineering domain, and we know that there are different kind of problem which we required HPC, like solving the turbulence problem, and some of the CFD problems, they are very large in size. They can have million of cells, and we cannot solve this kind of problem on desktop or laptop. And for the large problem, what we do, we divide the workload into a small number of nodes, and then divide and transfer data across the node. And all these are solved, and then interconnect bandwidth. Interconnect, it helps to do the computation and transfer data across the nodes. And that's how this HPC helps in doing the computation. As we talked that the different when we solve turbulence problem using DNS, or we want to solve a combustion problem with like for IC engine or for boiler, which may have the very small time step of the order of 10 to the minus 5 to 10 to the minus second, and if we want to resolve the combustion phenomena, and then we need this HPC computing facility. Or suppose you want to do the external flow over the aircraft or a car or the complete vehicle. For that we need the HPC facility. In the CFD domain, that where we can use this HPC, that aerospace, automotive, chemical reaction including combustion, environmental, engineering and process industries, when we want to solve any problem using LES or DNS or turbulence research type of any problem. So this basically it shows your flow over the car. And when we want to show flow over aircraft, for this kind of problem, we need the HPC. At CDEC, we have ported, optimized, and developed CFD application on HPC platform using the following platform, that GP GPU, and for this that CUDA platform is supported by NVIDIA. The Intel mic, it is a co-processor, and it is we have Garuda grid. In the GPU computing, traditionally this GPU it was used for previously for graphics rendering. Now this now we are using GPU for computation as well, because this the programming environment is the CUDA. So in the CUDA, it is a parallel programming platform in which is developed by NVIDIA, and it has CUDA compiler as well as that CUDA accelerated libraries that can be used. And this programming, it can be done using OpenCL, OpenSSE. These are the programming environment. The advantage of CUDA, the GPU, is that it uses less power as compared to the conventional CPU nodes. If you compare the power consumption for the CPU nodes versus the GPU, then you will find that the power consumption per flops is less in the GPU as compared to the CPU. We have deployed this OpenFOAM on the Intel Xeon this host processor, and we have run this lead driven cavity. As you know, this is a standard benchmark problem, and we have got a scale up to 768 processor. So suppose actually this was a 50 million problem. So suppose if you want to solve a very large problem of the order of 50 million. So for this this type of solving such a large problem, you need 1,000 cores kind of computing facility where you can solve the problem in the less time. You must be knowing about the OpenFOAM because it is a open source CFD software, and it is available on CPU as well as on the parallel computing platform. This problem that you must be knowing about the Ahmed body. This Ahmed body problem, it was solved on the GPU, and for this, we use this the GPU card. It was this NVIDIA Tesla 5, which was having 512 cores, and we have got a scale up of 5 times as compared to the CPU. Here also, okay, just I think, sorry, it looks many slide got skipped. Okay. I don't know why this slide is. Okay. And on GPU, we have solved one heat conduction code that using ADI and Douglas, and as well as on GPU. And we on the GPU using CUDA, we have got 10x speed up. This on Intel Xeon platform, we can run the code on the different mode. One is native mode, and another is offload mode, and another is symmetric mode. So this problem was solved purely on the Xeon Phi. As I told you that Xeon Phi, it is a coprocessor, and we solve 1 million grid point. And we have got speed up to say 150 cores on the Xeon Phi. OpenFOAM actually we have deployed on that Garuda grid. As I told you that in the Garuda grid, the different computing resources were connected through this NCAN network, and for this, what we have done, at the local desktop, all the pre-processing and post-processing was done, and the job was submitted to the Garuda grid. It was solved on the Garuda grid, and again the solution was downloaded, and the post-processing was done again at the local machine. So this was that how we are solving a problem over the network at the computing resources which are located remotely. For aerospace, in the aerospace, we have used HPC for solving external airflow problems, internal airflow problem, diffuser, combustor, and to study the fluid flow behavior in multi-stage compressor to determine stall and surge. We have used this for the axial flow compressor. We have tried to determine the condition of stall and surge. And in the axial flow compressor, we have developed the CFD model, parallel CFD model, which can determine where the stall happens and where the surge happens. Because if the flow rate is small, that due to flow separation, a stall phenomena happens. And if the flow rate or the mass flow rate is high, then due to shocks, the compressor is choked, and which reduces the compressor. And this we have studied using developing the CFD model. And just to give you idea that we have studied the complete stator using that parallel CFD model that we developed at CDAC. And this is the zoom view of the passage. We have studied 120 blades, and it was having 11.64 million cells. And here you can see that how when we solve, say we have used 160 processors, and here you can see that how the computation time decreases as we increase the more number of processors. So basically this the HPC helps in solving a large size problem in less time. So that is what the advantage of HPC. This is the MAC contour at the 50% span of the blade. Another we have done using for the fire simulations, we have used that HPC computing facility. For this we have used that fire dynamics simulator. This is a open source CFD tool which is available in the public domain, and this is developed at NIST USA. It is available for everybody, so anyone can download it. And this basically it solves a form of Navier-Stokes equation of low speed, and basically it uses LES techniques. And it has a software that post processing is done using smoke view. This study we have carried out at for the multi-storied building. at the CTEC Pune. It has a 5-story building, and we have used fire dynamics simulator, and we tried to find out how the fire, if there is any source of fire, then how the fire spreads over the period of time. Yeah, these are some of the assumptions. I think some of the slides are. So this is how actually here you can see, sorry, actually some of the slides are not getting displayed properly. So actually before that there is a slide which shows how the fire, it is not coming up.
I think it is not playing the simulation.
I don't know. So basically, actually, this before that, actually, there was a previous slide which shows how the fire spreads over a period of time, and then when we use that a smoke detector and when the blower is activated, then actually this slide shows that how the smoke is removed from the building. So this is the combination of slide that how the first how the fire spreads, and then after that when we activate the blower, then how that smoke is removed. So basically it shows that that how we can use that FDS tool to control the smoke for the multi-story building. Same thing, this tool, it can be used for any kind of that public theater kind of things that, and based on that we can provide some exhaust facility and how to activate it. So here you can see that with the visibility after 900 seconds, what is the visibility and how the visibility changes when we implement the smoke management system. So that's how this the CFD helps us in locating or managing the smoke management system. This again, this we have run it on different up to from 4 processor to 256 processor, and we have got a speed up of say 20 times 20 times and we have got a parallel efficiency of 32 parallel efficiency of 32%. Okay. Oh, before going to concluding, actually, I would like to take up some questions that and then I would like to conclude it. So I think many of you may not be having background of HPC. So if you have any questions that how we can use HPC at your workplace for solving some of the large problems, that I will try to answer, because actually what I have told you that these are some of the typical problems we have solved using that HPC facility which is available at CDEC. At your end also, I think there are different open source. There are different open source CFD tools are available, like OpenFOAM, which is widely used in the academic community, and it has both. It has a parallel version as well as CPU version both. So this, as I told you in the previously, that we have used Yeah, as here you can see that we have deployed OpenFOAM on a large HPC cluster, and we have solved a problem of 50 million size. Similarly, if you want to solve any large size problem, which may be of the 10 million, 50 million, or 20 million size, this OpenFOAM CFD tool is available. It is open source CFD tool. It is available, freely available. You can download it, or even at CDEC also you can, academic people, they can access it, which is available. OpenFOAM has different version. It is, you can put it on desktop, or you can use it on the HPC cluster. So at CDEC we have deployed OpenFOAM on HPC cluster. Again, that OpenFOAM has different version. The parallel version, it can do computation across the CPU nodes as well as GPU nodes. You please try to understand that the GPU is basically, it is a on the node, on the HPC computing node, there is a facility to add the GPU node, GPU card. So basically it helps or it accelerates the computation. Similarly, on if there is some HPC node, then there is a facility to add what is called the Intel Xeon Phi card. So basically this card, it helps you in doing a very high-end computation at faster rate. So anyone who wants to do a faster computation for large size problem, they can use they need to use that parallel version of this OpenFOAM. I don't know how many of you are aware of parallel computing. Anybody can tell?
Participant, please, someone can share their view.
Have you? I think, have you heard the word called parallel computing? Parallel computation. So this term is synonymous with the high performance computing.
Yes, sir. We have heard of it.
Okay, so have you deployed this parallel computing for the solving a large size problem?
No, sir. Actually, we are in the process of collaborating with somebody like CDAC, or recently Government of India has started that mission, no, National Supercomputing Mission.
Correct. So actually in the National Supercomputing Mission, actually CDAC, we have installed different a large size HPC cluster. When we say HPC cluster, it has say we have deployed HPC cluster at IIT Varanasi, IIT Kharagpur, ISAR Pune. Here actually this HPC cluster, they have computing capability of the order of petaflop. Okay.
Yes,
So there the computing, and at this HPC cluster we have made some of the parallel computing CFD softwares like OpenFOAM. Okay, so any user, any academic user, if they want to solve any kind of problems, they can get account at CDAC, and they can run the problem using OpenFOAM. They can, yeah.
So what is the process for that? Like, if being an academic, if I want to access the computing capabilities at CDAC, like I basically want to run my particular problem on OpenFOAM, but my computational power is not sufficient for that. So
you can get the user test. Some technical affiliation is there. Some form need to be filled in, and that you can get the access of that supercomputing that facility. Actually, this is available for almost all the academic institutions. I think at the end of this email, at the end of the presentation, I will display the email where you can contact and then you can get the technical affiliation.
Thank you, sir. That will be helpful. Yeah, thank you.
So, any participants have the questions they would like to know how they would like to use HPC at their organization or their research work? Then I will try to answer, because I have given you the glimpse that how that at the CDAC we have used HPC for solving some of that problem, but number of problem which you people can think of, it can be enormous. I think some people would like to work in chemical engineering domain, some would like to work in aerospace domain, somebody would like to work in mechanical engineering domain. So if anybody has question, then I would like to answer how actually they can use this HPC and that CFD for solving their problems.
Sir, is it possible to connect the commercial software like ANSYS or something for high performance computing?
See, I will tell you one thing. See at CDAC we have commercial as well as what is called that open source both. And I think everybody knows what is called advantage and limitation of that each tools. Okay. Suppose if you want to solve a very what is called, I will say, if you want to design a product. Okay. If you want to design a product and then you want to do you have a very short amount of time. Then during that condition, I will definitely suggest that you go for some commercial tool. Okay. Okay. But the only thing is that it is very costly, expensive, and its parallel license, it goes in crores. Whereas that OpenFOAM, it is open source. You can get parallel license free of cost. But yes, the learning curve is a large very large in the OpenFOAM, because it requires a lot of tweaks and tricks to get the problem solved using OpenFOAM, because we have used both OpenFOAM and we have used ANSYS both. So sometimes we don't get very quick solution in the OpenFOAM, but yes, definitely for the academic people, those people who are supervising MTech thesis, or those faculties who are supervising PhD thesis, definitely they can opt for OpenFOAM, doing some research, finding some how it behaves, how you can optimize it. There is a lot of scope how you can optimize the OpenFOAM solver. Those things, those facilities you will not get in the ANSYS. So the answer is that yes, you can get ANSYS license, parallel license, but it costs in crores. Means that a 16 core license, it cost something around 1.5 crores. Whereas that OpenFOAM license, it is free of cost. Definitely, I will suggest academic people, they should explore OpenFOAM kind of tools, which is widely used across the globe.
Yes, sir. Thank you.
So, sir, I have a question.
Yes.
Hello.
Yes.
Sir,
have 1 minute. Have you got the answer of your question?
Yes, sir.
Okay.
So, can I ask?
Yes, please.
So, I wanted to ask: Are there any training programs from CDAC regarding this parallel? We will have to write some programs for GPUs and all. So, are there any training programs regarding the same from CDAC?
Training program, I think they have, CDAC has launched some parallel. You can check at the CDAC website. I think okay. I think otherwise there are some parallel you can check at the CDAC website. I think there it should be there.
Okay, sir. Sure.
Hmm?
Thank you. Yes, sir.
Okay.
Yes, sir.
Okay. Next question.
Participant, please, if you have some question, please ask. Yeah, Dr. Vikas, sir, I think you can continue. Hello.
Yes. Yes, somebody asked about this, that how actually you can get CETA computing facility. So I think user here you can note down that basically there is NPSF technical application scheme which provides supercomputing facility to various industries as well as academic and R&D institution for the diverse application for supercomputing power. And please note down that please you write down email to this NPSF help@cetec.in, and they will do that necessary. Okay.
Yes, sir. Can you put up in the chat box? Is it better
What?
for us? Can you
What?
put up this mail ID in the chat box? It is better for us.
Okay. It is
Yeah.
not visible. Let me see.
Yeah.
It's clearly visible.
Is it okay?
Yeah, got it, sir. Got it.
Okay. So where is my pen? Okay, so here I would like to summarize some of the things that I talked about. That HPC, it helps in solving a more realistic CFD problems, and it can also help you in optimizing design of equipment with reduction in development time. Because just during this lockdown period, we have designed some of the chip puller, because we were supposed to do some kind of experimental work we could not do. So basically this how this CFD modeling, it helps in optimizing design of the equipment with reduction in computing times. And this again further, this HPC, it helps in accelerating the CFD computation, which further reduce the design cycle of any equipment or process. Further, again, the scalability efficiency of the CFD code. Actually, this is the very important, and it plays a very important role in the performance of any applications. So if there is any CFD code is there, it is not necessary that suppose if you have a 100 core machine or 64 core machine, then it is not necessary that if you have a parallel version of code, then if you are on the 64 core, you will get a scale up of 64 times. It is not necessary. There are a number of factor which works that how your code is optimized, how it is well designed, and then only you get the scale up. And further, HPC of no use if your application doesn't scale. Suppose if you have written a program and if you have say 100 cores or 50 cores, And if you don't get a scale up of say at least 20 times or 30 times, then this code it may not be well appreciated. So along. Okay, so that for running that HPC applications, there should be a optimized configuration of hardware as well as software both, so that you can get advantage of that. Okay, so still I'm available for taking. I think a lot of time is there because Professor Sonone, he has planned for I think 1.5 hour session. So still I'm available for answering your questions.
So you can show those simulation which we are not able to see actually. So you can just this minimize this PPT, and can you show us that simulation again? That fire simulation and all those things.
Let me see, because actually those things were actually in slide modes only. Actually it was let me see. Is it visible, Professor Sonane?
No,
Is
sir,
it?
not visible. Not visible, sir.
Not visible.
You can again you can sharing, you can make it off, and again you can have a sharing on.
Okay. Let me see. Is it visible?
Yeah, slides are visible. Yes, sir.
Now here, can you see the animation of the how the fire is spreading?
No, sir. No.
A smoke spread is not visible. Not visible.
No, something is moving, but where it is not clearly visible. Not visible, sir.
So basically, this shows that how if there is a fire source, then how the smoke is spreading.
Achha, okay.
But it is not visible, no?
No, not visible, sir. Not visible.
Okay, so in the CFT, basically the academic people, you people can work on the two fronts. Either you can use OpenFOAM CFT tool as a base, and then you can deploy its parallel version. You can solve some that large size problem. That could be one approach. Other approach that could be that you can identify some of the that linear algebra library in the that OpenFOAM for different. It has different solvers like IcoFOAM, simple form solvers are there. So you can change the libraries. You can optimize the library. And then you can see how you get the speed up. Further, you can explore the different kind of schemes. If you want, you can add different numerical schemes also. So these are the things, these are the research work that you can take up using OpenFOAM on the HPC platform. And further, we still, I would like to get. I'm not sure whether many of your participants they have understood fully, because actually I moved very fast. Some of the slides were, I think, due to technical problem, it was not shown properly. But the whole thing is that the gist of thing is that we are saying that how you can use HPC computing, parallel computing, or high performance computing for solving a large problem in the computational fluid domain. And as I told you, OpenFOAM is a one CFD tool. Similarly, for this fire simulation, we have used another CFD tools, that is fire dynamics simulator. So this is again this software is also available in the public domain. You can download it. And currently we are, in addition to building, currently we are also working on the that predicting the spread of forest fire. Because I think you in the recently, I think still you in the recent news also you have seen that in the California the forest fire is spreading at very rapid rate. So currently we are working on that forest predicting how the forest fire will spread. And for this again, actually we are using two tools for that. One is the WFDS, which is a what is called from the FDS only, and another tool is called the WRF Fire. So WRF Fire again, actually this is it has integration with that weather research and forecasting model. It has a component called fire component is there. So we are exploring WRF Fire and WFDS tool for predicting the forest fire. In the forest, if there is a fire, then we should be able to tell that okay, after 1 hour where will be the location of the fire. Again we will also be using the HPC for this applications for the forest fire prediction.
Sir, also I have one question. If we develop some code, is it possible to connect with HPC?
See, if you write a code, then to connect to HPC, it has what is called you should the program should be parallelized. It should make use of say different codes, which means you can divide your job into I will say, like for example, if you have a 100 million grid size problem, right? If you have a 100 million grid size problem, and suppose you want to solve 1000 cores. If you want to say 100 million problem on 1000 cores, then what happens? Your program should be written in such a way that each core should solve 1 lakh grid problem, okay? And it should communicate to the next what is called next node.
Correct.
So that your program should be written in such a way that it should talk to the different nodes, and then somebody will collect the computation done by all the nodes, and then it will compile, and then finally some node will integrate. So your program should be written. This is what it is called the parallel program. So you should write but see, either nowadays what is happening, some automatic compiler is also there. So which will convert your program into parallel program. Okay. So with the Intel, there are some tools are there which will automatically detect that okay, your at some point of time in your program some loop is there, like for loop kind of things is there. So these things can be easily it can be made parallel. So it will divide and it will make your program parallel, but that program may not be the optimized one. So in order to make your program optimized one, you have to work, you have to see, you have to different what is called tools are there. That is called the profiler, debugger. So there, so profiler tools, it gives you idea, okay, at which point of time, how much time is computing in each operation, and based on that, you can optimize you can use the right function to what is called to minimize your computation time.
Okay. Okay.
Have you got answer?
Yes, sir. Yes, sir. Yes, sir.
Similarly,
But
that suppose you are planning for writing this what is called the fluid structure interaction problem, right? So if
yeah.
your problem is, suppose if your problem is sequential, if you have written a program sequential, then you have to convert your in order to make it parallel. Your program, it should be able to make use of a number of cores. Okay.
Correct.
Say you want to solve on say 100 cores. So your program should be written in such a way that you can divide your grids on the 100 cores, and everyone will do computation, and then it should be integratable.
Correct. Got it, sir.
Okay.
Yes, sir. Yes, sir.
Similarly, many of the basically in solving CFD, we use different kind of that linear algebra libraries are there. Okay, many people are working on this linear algebra library. So they are trying to optimize it so that it takes the minimum storage, minimum memory, and it do the faster computation. Different kind of libraries. See, even with I have not told you many of things because see the OpenFOAM, it has a standard libraries there. I have not presented. We have integrated some of the library that's called, you can go, that PETC library is there. So using PETC library, we get even with the standard OpenFOAM solver, we get a scale up of 30%, 40% more speed as compared to the normal standard solver which is available in the OpenFOAM. So this way you can identify the most either if you are a good mathematician, you can write a good algebra library, and then the advantage of OpenFOAM is that you can write something and you can integrate with the OpenFOAM. Whereas in the case of ANSYS, for it has a limited scope, but but in the case of OpenFOAM, you can write or you can identify the library, third-party library, and you can integrate it.
Okay.
Hello, Vikas sir.
Yes.
Yeah.
Yeah, I'm Umesh Poddar from Pune.
Yes. Which is can I tell you? Can you please tell me the name of institute also?
Yeah, my name is Dr. Umesh Poddar. I'm from Pimpri Chinchwad College of Engineering, Pune.
Okay. Yes.
Yeah, which is situated in Nigdi.
Yes.
Okay.
Tell me.
Whenever we handle the turbulent flow, we generally prefer, especially in the academic community, the RANS modeling. Okay, because it's we can say the limitation. Why not we use the LES or the DNS because of the high computational power. But is it possible to handle this LES and the DNS with the help of CDAC facility?
Yeah, at CDAC, yeah, it depends on actually. Do you have basically do you have a code which can solve LES or DNS? If you have code, definitely you can get access. You can try solve it.
Okay, and is it possible with the commercial software?
See, I told you at CDAC we have deployed OpenFOAM CFD software on the HPC cluster, so you can access it. At HPC cluster, we have not deployed ANSYS Fluent. Okay.
Okay.
So that the other user may not get access of that.
Okay.
But yes, in the OpenFOAM also LES module is there that you can solve it.
Okay. Thank you. Sir.
And I will give you one idea. Professor Mahendra Verma from IIT Kanpur.
Yeah.
If you can search his what is called web page, Professor Mahendra Verma. He is from Department of Physics.
Okay.
He has written DNS code.
Okay.
And many people in the academic fraternity, they are using that code. So it is a spectral based DNS code. So if you want to solve some DNS problem, you in the turbulence, for solving turbulence or understanding turbulence, you can use that Professor Mahendra Verma code.
Surely, sir. Thank you very much. Yeah.
Okay. Yes. Next question, please.
Any other questions from participant, please?
It looks like many of the participants they have not understood my presentation.
No, it's a slightly higher level of understanding is required now for API. Itself is a CFD is a heavy dose, and again in the CFD again we
I
have
don't know. Otherwise I moved very fast or what? My pace was very fast. Looks like that.
no, that was decent actually. Only we are not able to see the animation. That's it. What you want to show?
You could not see the animation. Okay, unfortunately, I think.
Otherwise, no issue as such. If the participant don't have any say, you can say questions. So
Check this. This animation is coming. Something is black. Smoke is moving. No.
unfortunately, we are not able to see. That is a problem. It may be the connectivity, net connectivity.
I don't know.
It's okay, no problem, sir. Hello.
Okay. Yes. Yeah.
No,
Yes,
no problem. Okay.
Participants, do you have any questions which you think that how you can use SPC at your organization? How you can use solving that you using OpenFOAM or using HPC platform? We can guide you that how you can do that. I think you have got that email address where you can contact CDEC for accessing the HPC computing resources. Hello? Hello? Any participants have any questions? No, not getting any response.
I think, sir, there is no question from participant. So, thank you very much, sir, for your session. We got to know a lot of things about CDAC. So, of course, I request participant if they start working in the CFD field, and of course, they definitely come across the larger computational side. So, either that time they can contact, or even if you can try and do something, you can say MPI or parallel coding sort of things if they are planning. So the CDAC can definitely help them out. Sir,
Yes.
thank you very much, sir. Dr. Vikas Kumar, sir.
Yes.
Yes, sir. Thank you very much for your session, sir.
Unfortunately, that animation.
No, okay, sir. But we got a lot of insight regarding CDAC, its activity, because that must be known to the people, na. and that must be known to our CFD community, so that we can use at least or at least try to attempt to use it. Yes, sir. Thank you very much.
Okay, thanks, Professor Sonani, for providing the opportunity to speak to the participants.
Yes, sir. Yes, sir. Thank you very much, sir.
Okay.
Okay, sir.
Can I disconnect?